Last session, we sort of switched the topic a little bit about AutoML, which was no longer about finding the best architecture, but also about finding the best type of data augmentation. And we introduced the ideas of AutoAugment, which are borrowing the same ideas that you have a controller. It is gonna propose to you what type of operations, what type of data augmentation you need to do on your data set. You train an architecture on the augmented data set that's going to give you a reward in terms of your accuracy, and you can use that signal to update your controller. And out of this process, you would end up with an augmentation policy. But you are doing this, first of all, you have around 30 choices that you are making to augment your data. So the search space is huge, it's 10 to the power 32. And there is also this observation that if you want to do some transfer to a different data set and find the best augmentation policy for that data set, for instance, if your data set is ImageNet, you need to work with a smaller data set precisely for this reason, that you have around 30 softmaxes and your search space is huge. So you need to work with a proxy task, for instance, CFAR10, come up with your augmentation policy, and then use the same augmentation policy that you found for CFAR10 and apply it to ImageNet. And maybe this is not optimal. And the bottleneck is having 30 choices. Can we actually reduce that? Can we actually reduce that to perhaps 2 choices? And then you can have a dedicated augmentation policy for ImageNet or any other type of data set that you have. And that's the ideas of RandAugment. What do you want to do? What is the objective? The objective is to reduce the computational expense, to reduce your search space, and do your search in that smaller search space. And in that way, you're going to be able to get rid of your proxy task. And therefore, you're trying to find an augmentation policy which doesn't depend on a proxy task. And as I mentioned, something like AutoAugment, you have more than 30 plus choices. It was actually 30. And that's why you needed to have a recurrent neural network proposing to you what type of augmentation policy to choose. And the idea is that you want to simplify the search space, make it smaller. Like before, you have your PIL package or PIL library from Python image library that you can use to give you these sorts of transformations like identity, rotation, sharpness, translating the X direction, translating the Y direction, adjust the contrast, etc. Previously, you were actually looking for the best one among these. Now you're just gonna choose randomly according to a uniform distribution from this set. So there is no choice to be made anymore. So you're just randomly selecting one of them. And not only that, previously your neural network, your recurrent neural network, the controller, had to output probabilities of applying, for instance, rotation. Here, that probability is always 1/k. So there is no choice to be made there. So now you're reducing these 30 parameters to nothing for now. So you're just randomly selecting one of these operations to do on your image. But then you introduce a hyperparameter, and this is giving you one choice. What should be the number of transformations that you're going to do on an image? Maybe 1 transformation, or maybe 3 transformations. Like do a rotation, translating the X direction, and then adjust the contrast. So N is a hyperparameter that you need to find out. And previously, for each one of these operations, for instance, rotation, you could have the angle of your rotation to be normalized to be a number from 0 to 10. And that was the scale of the rotation. How much do you want to rotate? Now you're going to use only one number for all of these operations. And that's going to be your M. It's another hyperparameter. So you're going to use a single global distortion. And if that number M ends up to be 5, you're going to use 5 for all of these, regardless of whether you're translating or whether you're adjusting the contrast or brightness. Now you have 2 hyperparameters. It's small. It is much smaller than having 30 parameters. Therefore, you can do a simple grid search. So you're going to put a grid on M and N, and for every single point on that grid, you're going to go ahead and measure the reward, measure your accuracy. So your M could be one of your axes, N could be another axis. You put a grid, and for every single point on that grid, you're finding the best. You're finding a reward. Now that you have all of your options in front of you, in addition to how good they are, you're just going to choose the best one. And that's going to give you the best M and N. So there is no need for a recurrent neural network, for a controller. There is no need for reinforcement learning. A simple grid search is going to do the work for us because the search space is small. Okay. And what do you get out of it? This was RandAugment. You were finding it using a proxy task for ResNet. You were testing it on ImageNet, and that was giving you this much accuracy for top 1 and top 5 accuracies. RandAugment is giving you the same numbers, but what is cool now, you can change your architecture, and it turns out that your augmentation policy depends on the architecture and actually the data that you're using. For EfficientNet, you can actually do better for different versions of it. But what is the intuition behind this? Why are we doing this? Why do we want to get rid of the proxy task? Here is the intuition. There are some systematic failures when you're using some proxy task. What are they? The magnitude of your augmentation, in this case M, depends on the model, the size of the model that you have in front of you, and you're actually training data. So it's training data and model dependent. Let's see why. Let's do an experiment on CFAR10. We're going to use wide residual networks with different widening factors. For instance, you can have a smaller wide residual network, it's 28 layers deep, make it a little bit wider, change your widening factor to 7 or 10, and for each one of them, test your distortion magnitude. And you're going even beyond 10. Maybe your distortion could go up until 25 or more. And then you're trying to find the best distortion magnitude. You are trying out everything. This is similar to the grid search that we were doing here for different architectures. And for the blue one, which has a widening factor of 2, the best distortion magnitude ends up to be 11. So you have a 2 here. The corresponding optimal distortion magnitude is going to end up being 11. For this magenta curve, the widening factor being 7, the best one is going to end up being 15. So for 7, you have the corresponding number being 15, the optimal distortion magnitude. Similarly, for widening factor being 10, the best magnitude is ending up being 20 or 19. Okay, so far so good. So it turns out that as you increase your widening parameter, as you have more and more parameters in your model, as you make your model bigger and bigger, you need to distort more and more. You have a similar observation for your data size. If your data size is around 1K, you need to distort less. If it is around 4K, distort a little bit more. If it's around 10K, you need to distort even more. So there's an increasing pattern again in terms of your training data size. And that's going to give you different optimal distortion magnitudes. So that's this observation. Optimal magnitude of augmentation depends on the size of the model. That's this curve here, and the training size. And larger models in general need more distortions. Maybe because they are larger, you need to distort them more, do more data augmentation for them to be regularized. And a similar pattern happens when you have larger data sets. Whenever you have larger data sets, maybe as you distort more, you are being less sensitive to those huge distortions. And that's why, because of these 2 reasons, because of the dependence of your augmentation strength on the data set size and model size, you need to get rid of the proxy task. You cannot say that I'm going to find the best augmentation policy on CFAR10 and then apply it to ImageNet, apply the same architecture. But there's a catch here, the same augmentation, but there is a catch. ImageNet is big enough that you cannot keep exploring 30 plus more parameters. That's why you need to reduce your search space. So there is no free lunch again. If you want to have a dedicated augmentation policy for ImageNet, you cannot work with a lot of flexibility or a lot of degrees of freedom. Because each time that you're training a neural network on ImageNet, that's going to take around in the best case scenario one day, if you have enough hardware and resources in front of you. That's why you're going to reduce your search space to 2 only and do a simple grid search. And these augmentation policies, we are going to keep using them in the future. Somebody found it for us, and then we are just going to use them. Okay, so we don't have to find them from scratch ourselves, but at least we know what we're using. Any questions about RandAugment? Was everything clear? Okay, perfect. So with that, we can close the chapter of AutoML.